verilog. Verilog is a verification language. It is also a simulation means we will perform the simulation of our circuit. Like this is our circuit. This part is implementing some functionality. It can be, let us suppose, a simple example, it can be adder, multiplier, or any type of circuit, and we want to simulate it. Simulate means we will see it is operation, rather than having a prototype in the design in the available. We can just simulate it as a prototype, and with that we will check its functionality, whether the design is working according to the functionality, according to the specification. So this is simulation, and verification comes in this only means we are verifying whether the output that is producing by this DUT means design under test means this circuit and the character outputs. We will compare both, and we will see that we will verify the circuit's functionality. And also this verilog is a synthesis language. Synthesis. So what we mean by synthesis? Synthesis means here let us suppose we put C is equal to A plus B. So we are actually simulating the adder operation where A is one input, B is one input, and the output will be in the C. So by this we can simulate whether we are able to achieve this with respect to some timing constraint, or means the functionality should be validated here. But when we go for synthesis, we check whether, like, how this particular C is equal to A plus B, what type of adder will be synthesizer. Like when we get a netlist means the it is a type of structure where we are having this design in terms of the actual gates. Okay, so when we get this netlist, so we will by the synthesis will transform this particular statement into the actual gates, and by these gates this synthesis will actually there are different types of adders. It can be fast, there are fast adders, there are carry save adder, there are multiple type of adders. So ripple carry adder is there. So what type of adder this synthesis will transform this particular statement, so that is done by this synthesis. So there are some statements that is correct in terms of the simulation, but that are not correct in terms of the synthesis. Like we can take the example of for I is equal to 0, I is less than n, I plus bigger than n. So this is correct. This is correct in terms of the simulation. But this code is not synthesizable. Means there is no hardware. There is no hardware for this. It is not synthesizable. This for loop is not synthesizable code. Okay. So now we will see how we design our circuit. Let us suppose we have to design the adder. We know the adder has some truth table. What that truth table means? It says that it's functionality. Like if you are having inputs as A and B, these are the inputs to the adder. We have to perform the add of these two inputs, and the output will be C. Output will be as sum and the carry. What does carry mean? Means if the addition of these two numbers does not fit in the width of our design, means we will be specific with the number of bits we have for this particular sum. We'll be specific with that. Let us suppose we have 4 bits for this. Let us suppose this is 4 bits, this is 4 bits. If we got the 4 bits number as this, so we will get a carry here. So this carry will be here. So C out will be 1 here. So by carry we mean that we are not able to accommodate that the sum of two numbers in the sum variable, or we can say register. So with that we see that now we have generated the carry. Okay, so we have adder here. It has two inputs, one is A, one is B, and the output is sum and carry out. By this carry out we will be able to know our result is incorrect, because we have generated the carry. The actual result needs to be modified to get the correct result. Okay, so now we have to design this. Okay, so there will be designer. There will be some designer, RTL designer. He will write the code for this adder. Some way he will perform this C is equal to A plus B. Let us suppose he write only this way, C is equal to A plus B. And now we need to test this. C is equal to, this is DUT. This is done by the RTL designer. Okay, RTL designer designs the C is equal to A plus B. And here is the verification person. He has to verify. He has to write all the test cases. Test cases or test harness we can say. He has to put this all possibilities of A, all possibilities of B, and all like X, Z. He has to put everything 0, 1, X, and its combinations for this both of these. And C, how C is differing with respect to the correct output. If it is coming same, we will say that this design is correct. It is correct. Now it can go for the further steps. What does further steps mean? Synthesis. Now we will synthesize design. When we synthesize this design, after that also we need to do the verification. Why? Because the netlist that we got might be the synthesis compiler has done some modifications in the design, and our output is not coming correct. So we need to do the verification of the design after this netlist also. So the verification will be at 2 times. At the simulation we will check the code, the algorithm that we have written for solving the problem, whether that is correct. And at the time of getting the netlist, so we have to verify at that time also. So with that we will require the verification at 2 stages till now. After that we might require also, but till now stage. After simulation we need verification, and means we have written some code, RTL code. We verify this. We will simulate the design. Okay, and we are not performing the synthesis here. We don't care how synthesis will work at time of RTL simulation. We don't care for synthesis. But when we perform the synthesis, we actually care whether the netlist is performing correctly according to the specifications. Okay, so